So I'm going to tell you about fully homomorphic encryption, actually two variants of fully homomorphic encryption. I figured fully homomorphic encryption is like too short for a 15-minute talk. So in fact, I'll start with that. That'll be like the first 10 minutes. And then I'll tell you actually about two variants of it, multi-key FHE and spooky fully homomorphic encryption. I'll tell you what these are. So this is actually not a survey talk. I'll talk about some latest results, but it should be real accessible. So please ask questions if anything's not clear. OK, and the talk will roughly be about these three concepts, fully homomorphic encryption, then building on that, something called multi-key FHE, and building on that, something called spooky encryption. And the talk will be in roughly three parts. So the first part, I'll tell you what these things are. Then I'll tell you how to construct them. And I'll tell you about some applications, like why do you want these? OK, so let's start with the what. What are these things? So let's start with fully homomorphic encryption. How many of you have heard of fully homomorphic encryption? OK, most, but not all. So I'll just tell you a really brief description. So it's an idea that's been around for a long time, since the people have wanted to do this since the late 70s. But it's only been something that we've known how to do since very recently. And the idea is we have some user. The user has some data X. And the user wants to store this data on the cloud, but you don't trust the cloud. So the user will encrypt the data, select some public key secret key pair, and encrypt X with the public key, send the encryption of X to the cloud. So this is great. The cloud doesn't learn anything. But now the user wants the cloud to actually do something useful with this data, compute some function over it. So you want the cloud to evaluate some function of the data. Of course, the data is encrypted. And so what we'd like is for the cloud to be able to compute some function over the data by actually operating on the ciphertext. So manipulate the ciphertext and output some ciphertext C star, which is an encryption of f of x. So if you decrypt C star, you get f of x. So by manipulating on the ciphertext, you're really operating on the plain text. That's the goal here. That's why it's called fully homomorphic encryption. Actually, usually we want a generalization of this, so the user doesn't just encrypt one value in one shot. Maybe it encrypts many values one at a time, or in fact, you can think of this as a bit encryption scheme, so you encrypt many bits one at a time. You send all of the encrypted bits to the cloud, and the cloud can evaluate a function on all of these different ciphertexts. Okay, and then you get out one ciphertext which encrypts the output of the function. So this is fully homomorphic encryption. The goal here usually is that the ciphertext should be short, much shorter than, let's say, the size of the input data or the complexity of this function. So it's really efficient for the user to decrypt and get the function output at the end. Okay. So this is the first primitive we'll look at. The second primitive is an extension of this that is called multi-key FHE. It was introduced in a work by Lopez, Tromer, and Vinod a little more recently. And so here we don't have just one user. We have actually n different users. And these users have totally independent public key secret keys. They don't coordinate with each other. Each user chooses his own key pair. And they have their own inputs. They encrypt them separately and send these ciphertexts to the cloud. So now you still have n ciphertexts like you had before, but they're under different keys. They're not under the same key. And what we'd like is still for the cloud to be able to apply some operation to manipulate these ciphertexts and output an encryption of f of x1 up to xn. Okay, so we want to make sure that this ciphertext decrypts to f of x. But under what key? Well, it should be obvious that it shouldn't be under any one of these keys, because if it was, you wouldn't have security. If the cloud was able to get C star to be an encryption of f of all of these inputs under, let's say, secret key 2, then that means that party 2 would learn something about the input of party 1 without having the secret key, right? So that shouldn't happen. So by security, you know that no individual user should be able to decrypt the ciphertext. Instead, what we want to require is that somehow it's an encryption under the secret keys of all the users. So if they all come together, there's a way to combine the secret key of all these different people and get the output f of x. In fact, usually we want something additional, an additional goal here, which is that there's some nice way to do this decryption operation in a distributed way without the parties just revealing the secret key to each other. In some way that hides the secret key but reveals f of x. There should be some nice protocol to do this decryption. And so what I'll tell you about in this talk, so this concept of multi-key FHE was, the first construction was actually given in this work by Lopez al al. Under a somewhat non-standard assumption called the entrant assumption. So in this talk, I'll tell you about a scheme based on a more standard assumption called learning with errors. And I'll tell you also how to do the distributed decryption in a nice way, actually. So each party just publishes some partial decryption, you combine them, and you get out the output. And one of the applications that we'll discuss is this gives you a nice way to do two-round multi-party computation. So that's a major application of this. OK. And so the last primitive that we'll talk about is called spooky fully homomorphic encryption. I'll tell you why the name's spooky in a little bit. But the setup here is sort of the same as before. So we again have n users. And again, they have different inputs. They're going to choose completely independent public key secret key pairs and encrypt it, send it to the cloud. So far, this is the exact same setup as multi-key FHE. But now, instead of the cloud outputting one ciphertext, we want the cloud to be able to operate these n ciphertexts and output n new ciphertexts, C1 prime, C2 prime, Cn prime, for each of the n users separately. The n users will decrypt and get out some values y1 up to yn. So we're starting with encryptions of x1 up to xn under different keys. We want to manipulate them and get encryptions of y1 up to yn under the same keys, under the corresponding keys. Okay, that's the goal here. And I didn't tell you what y1, yn should be, but that's actually the question here. Question is, we're taking encryption of x1, xn, we're creating encryption of y1, yn, and the question is, what kind of relationships between x1, xn and y1, yn can we ensure? Okay, so the goal is to do something interesting. Let's see what we can do. And so if you start thinking about it, one thing you'll notice very easily is that the relationship is something that, called no signaling, which means that, for example, y1 should not depend on, let's say, x2. Because if it did, it means you're breaking semantic security. Without having the secret key for party 2, you're learning something. Party 1 will be learning something about x2, right? In fact, more generally, any subset of the yi's cannot depend on the xj's that are not in that set. Okay, so this is called no signaling. You cannot actually transfer information from one set of public keys into a disjoint set, into a different set. The other thing you notice is that if this encryption scheme is actually fully homomorphic, just fully homomorphic encryption, then you can implement any arbitrary local strategies where each yi is an arbitrary function of the corresponding xi. Okay, so y1 is a function of x1, yn is a different function of xn. So this you can do, this you can do. The question is this the full picture? And the answer is, it's actually not necessarily the full picture. There might be strategies, there might be relationships which are neither signaling nor local. And the question is, can we achieve such relationships? Just to give you an example, because it's always confusing, what do I mean? How can there be something in between? Here's something specific. So for example, in the case of n equals 2, imagine I want y1 and y2 to be two random values subject to their XOR being, let's say, the AND of x1 and x2. Okay, so now y1 is uniformly random. It does not depend on x2 at all. The distribution of y1 doesn't tell you, it's the same no matter what x2 is. Same thing for y2, the marginal distribution. So it satisfies this type of a relationship is no signaling, but it's not local. You can check easily that any local relationship cannot satisfy this. So the question is, can you build an encryption scheme that supports where you can do an evaluation that allows you to do things like this? And so this was a question that was first asked by Moni and Cynthia et al., where they asked this question because there was actually a proposed scheme, cryptographic scheme, for something called succinct arguments, where it relied, the proposed scheme relied on the fact that you cannot do things like this implicitly. Okay, and so they noticed, they observed that actually if you could do things like this, that scheme would not be secure. And they asked the question, are there schemes that allow you to do strategies that are neither local nor signaling? And so they called that type of relationship spooky, so let me tell you why. And it's by physical analogy to something that happens in quantum mechanics. So here's an analogy, a physical analogy. Imagine you have two users or two people standing on different planets, light years apart. They can't talk to each other. They don't have the time. And they get inputs x1 and x2 at roughly the same time, and they have to give some outputs y1 and y2. Okay? And again, you can ask what kind of relationships between y1, y2, and x1, x2 can they achieve? And so in this case, this has nothing to do with encryption. This is a physical scenario. But again, if you believe that faster than light communication is impossible, which is one of the properties of the physical world we believe in, you cannot do signaling strategies. So y2 cannot depend on x1, y1 cannot depend on x2. Again, you can do local strategies. That's easy. Just agree on the strategy ahead of time. But it turns out that in the quantum world, if these two users have some entangled quantum state that they shared before they got on these planets, or maybe at some point they were on Earth, they got quantum state they made on these planets, then there are actually some non-local relationships that are achievable in using quantum mechanics. And so Einstein thought this was spooky, actually thought it was an argument against why quantum mechanics shouldn't work. And so that's why this thing is called, we call these types of relationships spooky. And the question is, so this talk has nothing to do with quantum, nothing about the physical world, but it says really in the world of encryption, is the world of encryption where one party gets encrypted inputs under different public keys, is that more like the classical setting where you can only do local strategy, or is it more like the quantum setting, or maybe even beyond that, where you can do some of these spooky strategies that are neither local nor signaling? Okay, so that's the question. And so in this talk, I'll show you that actually, yes, there are fully homomorphic encryption schemes, again, under the learning with errors assumption, that can achieve a large class of these types of spooky relationships. In fact, something called additive function sharing, or AFS spooky. So for any function f, you can ensure that y1 up to yn are just an additive secret sharing of f of x1, xn. So in particular, that gives you like the thing you saw on the last slide, where y1 plus y1 XOR y2 is the AND of x1 and x2.
So y1 and y minus 1, or at least n minus 1 subset should reveal any information about
That's right. Exactly.
So since this is the most general, on the other hand, all the ends should reveal information.
That's right, but there might be other spooky relationships that are not of this form. I'm not claiming that this captures all spooky relationships, all relationships which are neither local nor signaling. But it's a large class of them, and again, we'll see that this actually has some application. In fact, well, one application of this is that you can think of this as a special type of multi-key fully homomorphic encryption. In multi-key FHE, the goal was to get just one ciphertext rather than n ciphertext. But you can think of these n ciphertexts as sort of one ciphertext, right? And then the way to decrypt it with all the keys is to decrypt them all individually and then XOR the output. So this is a special type of multi-key FHE where the decryption with n secret keys has this specific format. Yeah?
Is this class of spooky relations sufficient to break soundness of the protocol?
Yes. Yes, so one of the applications is that this gives you a counterexample to that proposed protocol that sort of relied on things not being spooky.
So what you really want is an FHE that you can only do local computations, right? Do you know?
You want that for that one case, which I'm not talking about, except I'm talking about a lot. But there are applications of actually where you want to be able to do spooky things. I'll mention, you know. Again, well, one is to multi-key FH. It's a special, which is we don't, yeah.
So this will have
it's on the last slide, so I'll mention some things about it. So okay, but I don't. Yeah.
If you can prove the result, and if you cannot prove the result, science will.
Okay, so the next part of the talk is how to do these things. So this is where we're going to have to get our hands dirty, roll up our sleeves, and do a little math. So, okay. So I'm going to start by telling you about actually a fully homomorphic encryption scheme, one by Gentry, Sahai, and Waters. It's a really nice one, really simple. It's only a few slides. You'll see exactly how to do fully homomorphic encryption. Then we'll see how to do a little more work to make it into multi-key FHE, and a little more work to make into this additive function sharing spooky. Probably we won't get to the last part, but we'll see. All right. So let's start with the learning with errors assumption. This is the assumption we're basing the security of the scheme on. So the assumption says that essential random linear equations noisy linear equations are indistinguishable from uniform. Or a little more concretely, we're going to start with the matrix B. In every other talk, this is called A, so don't be confused, but I'll call it B for a reason. So we're going to start with the matrix B, which is like a fat, short matrix over ZQ. And we're going to take a linear combination of the rows of B and add some error. So error here is some small Gaussian. We can talk about the distribution, but for the purposes of this talk, just think of it as some random offset for each in each component of this vector, where this offset is much smaller. So this error vector has much smaller entries than Q. Like let's say they're between square root of Q, negative square root of Q, and positive square root of Q, or something like that. Okay, so the error is much smaller than Q. And we're gonna take this linear combination with the error, and we're gonna define a matrix which consists of the first n rows being the matrix B and the last row being this noisy linear combination. And the LW assumption says that this matrix, it's actually statistically far from uniform. A uniform matrix is very unlikely that the last row is close to a linear combination of the previous rows, but the assumption says it's a computation. You can't tell these distributions apart. This looks like a uniformly random matrix. Okay, that's LW. Okay, so here's our fully homomorphic encryption scheme by Gentry, Tsai, and Waters. So the public key is going to be matrix A, so I'm reserving A for this matrix, which is the matrix B, which is the random matrix, plus this last row, which is the noisy linear combination. And the secret key is going to be a vector consisting of S is the coefficient vector, so negative S and 1. And the main property you should remember about this is that just if you take the secret key and multiply by the public key, you get negative S times B plus SB. So that cancels out. You get E. So you get something which is roughly, you get something small, a small vector. And small things I'll ignore. I'll say they're like 0. I'll put these squiggly lines to like ignore small things. Okay. So this is the main property to remember between the public keys and the secret key. Secret key times public key, T times A, is close to 0. To encrypt a bit X under the public key A, you're going to take some random matrix R, which is a 0, 1 matrix. So all the entries are just zeros or ones. And you're going to do AR plus X times G, where G is some other matrix that I'll tell you about in a little bit, that'll have some properties. And again, this operation is done over ZQ, but remember the entries of R are short, just zeros and ones. Okay, so that's the encryption of a bit X. And the main property to remember about these ciphertexts is if you take the secret key times the ciphertext, so that's T times C, well, T times A is E, so you get ER. These are both short, so we can ignore that. So you essentially get something that's close to XTG, okay? So secret key times ciphertext is plain text X times the secret key times matrix G. That's the main property to remember. And this lets you decrypt. So by taking the secret key times the ciphertext, you get XTG. If X is 0, this is something small, close to 0. If X is 1, then TG, you'll have to trust me, it's not close to 0. Okay, so that's how you decrypt. Okay, and the security of this encryption actually follows right away from the LW assumption. So if you see the public key and the ciphertext, well, by the LW assumption, I can replace this matrix A with uniform. So there's like uniform and uniform times R plus XG. And by something called the leftover hash lemma, you can actually say statistically U times R is random, even given U. Okay, so that's it. That's the proof of security. Okay, so I didn't tell you what this matrix G was. So we need to know something about it in order to be able to do the homomorphic operation. So this is called the gadget matrix. And the only thing you need to know about it is that there's an efficient function G inverse. So there's an abuse of notation. G inverse is not a matrix inverse. It's a function. It's a function that takes input a vector over an n-dimensional vector and outputs an m-dimensional vector, but of zeros and ones. And it has the property that for all y, G times G inverse of y is equal to y. So actually, there's many solutions to this equation, Gx equals y. There are many solutions x. And G inverse of y just happens to find one of the solutions, which is short. The entries are just 0, 1. Okay? That's the only thing you need to know. And there's an implementation using bit decomposition. Never mind. Let me skip that. There's actually different ways to do this, but this is all you need to know. Okay, so with this gadget matrix, let me show you how to do the homomorphic operation. So I want to make sure that if you have encryptions of bits x1 up to xn, you can evaluate any functions over these bits by manipulating the ciphertext. Well, it turns out all you need to do is compute AND and XOR, or multiplication and addition. These are complete operations. So let's see that. If you have an encryption of 2 bits x1 and x2, I want to create an encryption of x1 plus x2 and x1 times x2. So this is, we know that the ciphertext satisfies this property. To compute an addition, you can just add the ciphertext. And you see that the right thing happens. So if you try to decrypt this new ciphertext C+, you just get, well, the sum of the 2 bits, x1 plus x2 tg. So the same, this invariant holds. Okay, multiplication is just slightly more complicated. So to multiply 2 ciphertexts, you just do C1 times G inverse of C2. Okay, and what happens? Well, if you look at the property, so what happens is if you try to decrypt this new ciphertext, well, you get T times C1, which is x1 Tg plus error times G inverse C2. The error and G inverse C2 are both small. That's the property of G inverse, it's just bits. So I can ignore this whole term, it's just something small. So this is like x1t times G inverse C2. The G inverse cancels out, you get just C2. And then TC2 is close to x2 Tg, right? So you get the right thing. So we maintain this invariant, and then to do a NAND, you just combine these 2 operations, essentially. Okay, so what happens here is that the ciphertext has some inherent notion of how noisy it is, which is sort of if you do this operation T times C, how close am I to xi Tg? What's the noise here? And what's the error when I try to decrypt? And as I do operations, the noise grows. So if I'm going to call the initial error n, then if I add 2 ciphertexts, my error blows up to 2n. If I multiply 2 ciphertexts, my error blows up by a factor of n plus 1. n plus 1 is like the dimension of the matrix, of the LW dimension. So the error grows as I do operations, which means I have to be careful as I'm evaluating some circuit homomorphically by doing these operations on ciphertext. The error keeps growing and growing. If I have d levels, if my circuit consists of d levels, the error at the end will be some exponential in d larger than it was in the beginning. But that's okay, I can handle that just by setting my modulus to be big enough so that this error is still much, much smaller than the modulus, and that way I can still decrypt correctly. Okay, and there's other ways to get around this problem using something called bootstrapping, which I'm not going to get into. Okay. So let's now see how to, so that's it, that's fully homomorphic encryption. Maybe it took a little more than 5 minutes, but now let's see how to make this into a multi-key scheme, multi-key homomorphic. So now my scenario is I have n parties that have totally independent public key, secret keys. So let's say the secret key of party I is Ti. And I'm going to define the expanded secret key to just be the concatenation of all of them. So just a bigger vector, just concatenate all the secret keys together. And my goal here will be to essentially take a ciphertext that's created by a single party, party I, and somehow convert it into an expanded multi-key ciphertext, which sort of has the same property as we had before, but just with respect to the bigger key. So I'm going to take a ciphertext that belongs only to one party and sort of expand it out into a multi-key ciphertext that is decryptable by the combined secret key of all the parties. So more concretely, I start with a ciphertext C that is, that's a good ciphertext for party I, and I want to expand it into ciphertext C hat, which satisfies the same property, but for the expanded secret key. And everything, all the dimensions blow up proportionately by this factor. Okay, so that's my goal. How do I go? And if I do that, if I'm able to do that, then I can just perform the same homomorphic operations on these expanded ciphertexts. So I'll take all the individual ciphertexts, expand them out, and then do the homomorphic operations the exact same way I did before. So I don't have to show you how to do homomorphic operations anymore. All I have to show you is how to do this expansion operation. Okay. Okay, so let's do this for just two parties, n equals 2, and I claim everything extends naturally. You'll have to trust me. Okay, so I start out with two different public key secret keys for two different parties. These are not really very related to each other, except there's some cheating. I am assumed that they both use the same matrix B. So this is just some randomness. I assume they actually have common randomness that they're sharing when they generate their public key secret keys. There's no trapdoor with this or anything like that, just assuming that everyone has access to common uniform randomness. Okay. And the way we're gonna do this is that each party's encryption, let's say the party 1 encryption of a bit X is gonna be a ciphertext of this form, plus some additional helper info that I'll tell you about in a little bit. That'll be useful. And remember, it satisfies this property. This was the main decryption property at ciphertext satisfy, right? So this is what happens if you try to decrypt C with T1. What happens if you try to decrypt C, the ciphertext of party 1, with T2, with the secret key of party 2? That's a strange thing to do. You're encrypting one party ciphertext with the wrong secret key. Why would you do it? But let's see what happens. Well, you do a little math. You actually end up getting almost the right thing. This is what we, if this was a ciphertext under party 2, this is what we'd want. Of course, you shouldn't get the right thing, right? Party 2 should not be able to decrypt party 1 ciphertext. So there happens to be this blinding factor, B1 minus B2R, where R is the randomness used to encrypt, used by party 1 to encrypt. But it has some nice structure. You almost get the right thing, except for this, this extra factor that you don't know how to get rid of. And you shouldn't be able to get rid of. Party 2 shouldn't be able to get rid of on its own. Okay, but this is going to be useful, this structure. And it's going to allow us to define the expanded ciphertext to be just a matrix that looks like this. So we're going to take C, put it in the top left corner, put it also on the bottom right corner, and then put some matrix D here. Okay, where D I'm going to call an unmasked term. So what happens if you try to decrypt C hat with the combined secret key T1, T2? Well, so T1C gives you the right thing, XT1G. So you get the right thing in the first half of the decryption vector. On the other hand, on the right side, you get T1D plus T2C. We know what T2C is. It's this thing, right? All we want is XT2G over here. Okay, so we want this to be equal to this. So it better be the case that T1D exactly kills this factor that we had over here. Okay, so that's our goal for the matrix D. Our goal now is, so there's two things I didn't define on this slide. Our goal is to create some helper information for the party 1 such that you will then be able to create a matrix D that has this property. Okay, so I'm just going to summarize. So again, our goal is just to create some helper information, and then later that helper information should let us create what I'll call an unmasked term D that has this property. Actually, why not just make D an encryption of this value? Can someone? Who does it? Exactly. The reason is that party 1 can't do it at encryption time because he doesn't know B2. He doesn't know the public key of party 2 isn't even around, right? So that's the only problem. And the solution is actually pretty simple. The idea is that party 1 is going to encrypt R using the same encryption scheme, component by component. Each component of this matrix R, 1 bit at a time. These are bits. Party 1 is just going to encrypt each of these bits. So I'm essentially taking a ciphertext and encrypting the randomness of the encryption randomness again.
So you're saying instead of encrypting B2 minus B1 times R, which I can't.
Exactly. I encrypt R.
And you later
And exactly. And then to create this matrix D, I'm essentially going to do the homomorphic operation on these ciphertexts to create an encryption of this. And that's my matrix D. So I'm skipping something. It's not, but this is roughly the idea.
So who's going to be computing D?
Huh? Who's computing D?
Yeah,
so good. So the ciphertext of party 1 is just the C and the helper information. So this is the and then later when you want to when you know who the parties are and you want to expand all ciphertext to be ciphertext of parties 1, expanded ciphertext for parties 1 and 2. So later when you find out the public key of party 2, you can expand out the ciphertext of party 1 and compute this matrix D.
So when you're roughly when you're ready to do the
computation,
Exactly.
you first expand the ciphertext, and that part is
Exactly. So first you collect all the ciphertext, and when you're ready to do homomorphic computation, at that point you know who all the parties are, what their public keys are, you expand them all out. That's it. Okay. So that's the whole idea. What about the distributed decryption? How do we decrypt this big ciphertext, this expanded ciphertext at the end? So again, now we have an expanded secret key T hat, we have an expanded ciphertext C hat, and they satisfy this relationship, the same relationship we had before on the small secret keys in ciphertext. Well, we could try to just decrypt by doing something like this, but that's inconvenient because then in the even if I reveal to you actually this decryption, you learn all the secret keys. So that's a bad idea. I want to make sure that somehow I'm able to decrypt the ciphertext in a distributed way without revealing the secret keys. So here's the idea. We're actually going to put this ciphertext. This is like a big fat ciphertext. We're going to put on a diet and convert it into just a single vector by multiplying by G inverse of this vector, W, which is just zeros, and Q over 2 at the end. Okay, something weird's going on, but let's see what happens. So if I do then try to just take the inner product of T and C hat, the diet ciphertext, what happens? I get this, right? This is my just expanding out the diet ciphertext. Well, I know TC is XTG times G inverse of W. G and G inverse cancels out, so I get X times TW. But T has well, W is all 0, so I only care about the very last component of T, which is a 1. Remember, T is always at a 1 at the end. So I get X times Q over 2. And then I can, just judging whether this is closer to 0 Q over 2, I can decrypt. Yeah, you're right. This was just an easy way to do it. But okay. But the nice thing is now I essentially take my expanded ciphertext, I put it on a diet, I get a 1 vector, and then to decrypt that, I just take the inner product of the expanded secret key and the expanded ciphertext, and then round. So I get X times Q over 2. I have to round whether it's closer to 0 Q over 2 to get X. So, yeah.
I didn't quite understand Vinod's question. He's suggesting a different way of preparing the diet?
I think if you understood this, then yeah, there's a different way to do the die just by picking out one column.
If you go non-black box and do how C hat goes, then you can do it much easier. You can do it one step less, but I think this is better.
If you understand this, then don't worry about Vinod's question.
This is already just one
That's right.
column of G hat inverse, right?
Yeah. This is good.
Okay.
Let's stick with this. Don't do alternatives. Okay. So what does that mean? That to decrypt C hat, we just C hat actually consists of n vectors, and to decrypt, you just take the sum of each secret key times the corresponding ciphertext individually, and then round. Well, that already looks a lot like what we wanted with spooky FHE, where the output of the homomorphic operation is not one ciphertext, but n ciphertext. Well, you can see what they would be. They would be the C1 up to Cn. Right? It almost looks the same. We'll see that's not quite true. There's an issue. But here you sort of do have n components, one for each party, and to decrypt it, each party does its own thing, but then you add it up and round. Okay, so that gives us a distributed decryption where each party just outputs its own partial decryption, its secret key inner product with its part of the ciphertext, and then you just sum them up and round. And hopefully this has some security. Like each party, it does, but I won't tell you exactly what security properties this satisfies. So, but at least you're not revealing the secret key in full. You're sort of only revealing partial decryptions. Yeah?
If you round and add, you actually get the wrong answer.
If you what?
If you round first, then you add, you get the wrong answer.
It's, yeah, that's a good, yes. Okay, and that's the whole next slide is going to be about that essentially. So you're sort of ruining my slides here, but thanks. Yeah, so actually that's exactly the point. So this gives us a way to do distributed decryption. Looks like what we wanted to do with spooky FHE, but there's a difference, and it's exactly what you said. So in multi-key, oops, all right, that's fine. In multi-key GSW FHE, so single key ciphertext has this format, and a multi-key ciphertext is just sort of has this format. So it's just a bigger version of the single key one. Just everything gets bigger. And so to decrypt the multi-key ciphertext, you sum up and then round, right? So, or to decrypt, you sum up and round. So to decrypt the multi-key one, you sum up and then round. What we want in spooky encryption is that that first each party decrypts. So actually first each party rounds its inner product of TI-CI, and then you sum. We want the decryptions to be an additive secret sharing. And the question is, you know, are these two the same thing? We want these to be equal. Well, it's like we can wish for it, doesn't make it true. So it's not. But it turns out it actually is in the special case when you just have two parties. Okay? So when you have two parties, this actually ends up to hold. So if you have two values, P1 and P2, think of that as the two inner products here that sum up to x times q over 2. And you first round and then sum. So if you first round and then sum, you get x. Then it happens to be the case that, sorry, I'm saying the wrong thing. So if you have these two values, P1 and P2, that are close to x times q over 2, so if you first added and then rounded, you would get x. Then it happens to be that if you first round and then add, you also get x. Okay, and here's like a visual proof by picture. So what happens if this holds? It means that if P1, so let's say x is 0, okay? So P1 plus P2 are equal to 0. That means they're on opposite sides of this half circle. Okay, they're sort of, so if P1 is here, P2 is here. If P1 is here, P2 is here. That means if I first round and then add, well, if P1 is here, P2 is here, they both round to 0, I get 0. If they're here and here, they both round to 1, I still get, I'm adding mod 2, I get 0, right? So first rounding and then adding mod 2 is the same as first adding mod q and then rounding. There's the only possible potential problem is there's some error. So P1 and P2 are not exactly 0. They're just close to 0. So the problem is if P1 is like somewhere here, like very close to the border, and P2 just happens to be on the other side of the border, then I mess up. But if Q is big and P1 and P2 are random places subject to this being the case, then this won't happen. And so you can with a couple of tricks, you can make sure that this will happen with probability 1 over square root of k. 1 over q. Yeah, and q can be exponential. So this will be negligible as long as q is exponential. Okay, so how much time do I have? Like 5 minutes? Oh, perfect, all right. Okay, so yeah.
So this is true if P1 and P2 are uniformly random.
Yeah.
But you're going to apply to P1 and P2 being the output of partial decryption whose statistical distribution made available.
Good. So I was hoping to sweep that under the rug. You're absolutely right. So so there's an easy way to re-randomize. We can publish some two random values that sum up to 0 in our public keys and just sort of add these together to like re-randomize them.
In the CRS.
Yeah. We actually sorry. So I'm going to. You're saying. I'm assuming that P1 and P2, I know they add up to 0, but I don't know where this holds if P1 is in a random place on the circle. It might not be. I'm just going to publish some value mod q in the sky and add them to both P1 and P2, or add it to P1 subtracted from P2, right? And then I do ensure that at least individually they're random. So then I sort of put them in random places on the circle subject to their sum being close to x times xq over 2. So yeah, it's a small trick that you need to do. It could be in the ciphertext. You're right. It could be, oh, well, then who picks it? But yeah, maybe the first party picks it. Yeah, yeah, you're right. So, okay. Okay, so that works for two parties. I have two-party spooky FHE. I want to do this for any number of parties. And it turns out there's actually a fairly simple trick that lets me go fairly generically from any two-party spooky, this additive function spooky FHE into n parties, convert from 2 to n. So again, let's see what we have. We have encryptions now of n bits under, or n values under n different public keys. We want to get encryptions of y1 up to yn such that their sum mod 2 is f of x1 xn.
You're saying this commutative rounding and
It doesn't hold for 3, yeah. So
you don't know another way to do it, which is sort of,
right, I don't know a way to do it like very directly using the algebra of the FHE scheme I showed you. Instead, I'm going to give you sort of a generic way to convert, to go from 2-party to n-party, which needs to do something different. Okay, so I have these encryptions of x1, I want to get encryption of y1, and subject to this constraint. And the idea of how to do this actually follows the multi-party computation protocol of GMW, if you know what that is. If you don't know, don't worry, I'll pretty much tell you. So the invariant is that we're going to do this computation of a circuit 1 gate at a time. And the invariant is that for each wire of the circuit, as we compute, we have encryptions of W. So for each wire that has some value W, we have encryptions of values W1, Wn, which are an additive secret sharing of W. Okay, so that's not what we have initially. Initially, we have encryptions of the bits x1, xn. They're not secret shared, but we can essentially take this encryption of x1 and then encrypt zeros for all the other parties. So that'll make sure that we have this for the input wires. Okay, that's how to just encrypt 0 for all the other parties. I didn't say it has to be a random secret sharing. I just want this to hold for correctness, right? So that'll make sure that I have this invariant for the input wires. Right? I'm just going to encrypt zeros to get some secret sharing of x1, x2, and xn separately. Okay, so I'm actually going from like n ciphertext to n times the number of inputs, like n squared ciphertext, right? Okay, so now if I have an addition gate that I'm trying to compute, well, I'm going to use the fact, so here's one property I want of this encryption scheme, that it's at least additively homomorphic for single key. So single key additive homomorphism, I can do that. So right, I'm just going to take the ciphertext and add them component-wise. Take the 2 vectors of ciphertext and add them component-wise. So that lets me compute an addition gate. What about a multiplication gate? Well, I'm going to rely on 2-party spooky. So I can multiply 2 values in a spooky way to do this whole multiplication. The idea is that, so I have encryptions of A1, AN that add up to A. I have encryptions of B1, BN that add up to B. Those are my 2 input wires. Let's say I'm doing multiplication, so I want to get encryptions of C1, Cn that add up to A times B. What I'm going to do is just, I'm going to create, so I'm going to sort of multiply each pair of values, AI, Bj. And with the spooky operation, I'll get 2 ciphertexts, so an encryption of Dij and Eij that add up to AI, Bj. Right? So I'll get an encryption for party I and an encryption under party J of these 2 values. And then I'm just going to sum up all the party I ciphertexts, sum up all the party J ciphertexts, so sum up all the ciphertexts for each party. And again, by just doing the algebra, this gives me an encryption of Ci such that the encryptions of these CIs add up to A times B. Okay? This is actually really what happens with GMW, where instead in GMW use oblivious transfer to do this multiplication, to create this sharing. Here I'm using the 2-party spooky operation. Here it's not interactive, right? So there's no parties here. This is all in my head, right? So I have these n ciphertexts. So yeah, I should make that clear. I have these n ciphertexts in the beginning, and I do all this as one person in my head. There's no parties. I'm just a single guy. I'm doing all these operations myself. And at the very
You're only using 2-key FHE, not
I'm using, so here I'm using, my assumption of this encryption scheme is that it's additively homomorphic for 1 key.
Yeah.
And 2-key spooky. So I can do I can multiply x1 times xi times yj and get 2 encryptions under party I and party j of 2 values that sum up to the product. Okay, so that's what I'm using here. So I can create Dij and Eij that sum up to AI Bj. Okay, this is really what happens in, sort of me doing GMW in my head. Okay, so let me tell you just very quickly about an application of this to 2-round multi-party computation. There's a couple of other applications to something called function secret sharing. It's something that came from a work of Yuval and Elat. And I think those are the only people in the room. and also gives you, so this is something you asked, it gives you a counterexample to this construction of succinct arguments.
Spooky encryption, the encryption of the white eyes, are they like n times the size of the original ciphertext? Or are they
No, let me think about it. No, they're not. So each ciphertext is exactly the same length as the original ciphertext. In fact, they look like they have the same. Yeah, they're just have the same look as the original ciphertext. Yeah, in the multi-key FHE, you're right. If I sort of think of it as a multi-key FHE, then my ciphertexts are n times bigger because they're like the concatenation of all the n ciphertexts for the individual parties. In the multi, if I think of it as a multi-key, in the intermediate representation, as I'm doing operations, things are big, but then at the end, I sort of take this big ciphertext and split it up into n small ciphertexts. So the ciphertexts I get at the end are the same look to them as the original ciphertext. Okay. So I'm just very briefly going to tell you about an application to multi-party computation. So you already heard about multi-party computation this morning. So we have some number of parties. They have inputs x1, x2, x3. And they want to compute some function f of these inputs without revealing the inputs to each other. So we want correctness. Everyone should compute the output of this function. And security, nothing else should be revealed. Right? So this guy doesn't want x2 to be revealed and so on. And I'm going to assume, we have n parties and any number of them can be corrupted. Okay, so the question is, I'm going to skip around a little. Question is, what's the best round complexity we could get? It's easy to say that one round is impossible. Question is, can you do it in 2 rounds? And so here's an easy way to do it in 2 rounds with multi-key FHE. It's actually a really simple protocol. Each party just chooses its own public key secret key pair, encrypts its input under its own public key, and sends out broadcast the public key and the ciphertext. Okay, so that's the first round. Each party just broadcasts the public key and the ciphertext. At the end of this round, you have all the ciphertext, all the public keys. You can now do the multi-key evaluation operation on these ciphertexts and get an encryption of the output of this function under all the secret keys. Right? So get this multi-key encryption of all the outputs. And now you just need to run some distribute decryption operation where each party partially decrypts the ciphertext to get the output of the function. And we saw how to do this in 1 round. So each party just needs to broadcast its own decryption, its own partial decryption of the ciphertext. In fact, if the multi-key FHE you use is in particular the spooky encryption, where this thing actually you can think of it as n separate ciphertexts, which are decrypted by each party separately. Then at the end of the first round, so you get this C star really consists of n ciphertexts, and each party just decrypts its own ciphertext individually. So at the end of the first round, you actually get an additive secret sharing of the output of the function. So you get a 1 round MPC at the end of which you don't get the output. You can't. 1 round MPC doesn't exist, but you get in 1 round you get a secret sharing of the output, and then the second round is just broadcast the shares and add them up to get the output. So it's a really nice way to do it.
So then this in CRS or there's no CRS?
Good. So this generic formulation doesn't have a CRS in it inherently, but the only way we know how to get this multi-key FHE and the spooky FHE from learning with errors does require CRS.
But it's not programmable CRS.
It's not. It's a totally random. This is even. It's a random string. Yeah. It's, sorry. It just we assume that there's some shared randomness that all the parties agree on.
Is it actually
Like
uniform random or is
It's uniformly random. It's the LW matrix. That's it. Like it's uniformly random.
So in the worst case, you just add 1 round and then everybody can.
Yeah.
So have broadcast chooses.
Yeah. In the semi-honest case, you can add 1 round where just one party chooses this. There's no trapdoors to it or anything. But it's a good question about CRS. So that actually brings up some, the.
Go back 1 slide just to the FHE slide. So what's the adversarial model here? This is
Yeah, this is semi-honest actually. So I'm assuming semi-honest adversary. We know we actually can't do. If you want to make this malicious, you can do that with NISX actually in the CRS model, with non-interactive zero knowledge. Okay. Yeah.
Were there any protocols of this form using other?
So.
That gave you this sort of 2-round broadcast?
So all we had before this, we had 3 rounds from LW using some similar type of style, some similar idea, and we had 2 rounds from indistinguishable obfuscation. So this was the first 2 rounds from like a standard assumption. Okay. So just let me pretty much finish up with just a couple of other results I wanted to mention. So one is, can you, Rachel's question, can you actually do this? Can you get multi-key or spooky encryption without a CRS? And this would imply a semi-honest, honest but curious multi-party computation, 2 rounds without a CRS. So we show that we can do this using indistinguishability obfuscation. You can actually build a multi-key and spooky encryption without a CRS. Question is, can you do it under nicer assumptions? We don't know. Huh?
De-randomization assumptions don't work?
Not that I know of. Yeah. Why do I care? Yeah. I want to get semi-honest multi-party computation without a CRS. Why? I don't know. Just I don't believe.
Can you get covert?
Huh? I don't like looking at sunspots to write my MPC or something, right? So
the term CRS is overloaded. This is the weakest form of CRS known to mankind.
Thank you, Yuval. So, yeah. Okay, so the other question, which was something I think Moni asked, can you actually build an encryption scheme, or maybe, I don't know, someone asked it, can you build an encryption scheme which is spooky free? So it actually explicitly disallows any non-local relationships. The only evaluation, if you take n ciphertext, operate on them, get n new ciphertext, the only relationship you can have is local. So we saw there exist schemes that allow spooky relationships. Are there schemes that explicitly are secure against them, don't allow them? So one sort of like smart-ass answer is that non-malleable encryption is spooky free, but it's not very interesting because for any application of this, you want like a homomorphic but spooky free encryption. Okay, so that's not very interesting. So you can construct spooky free encryption from succinct non-interactive arguments of knowledge. So it means like as a primitive, it makes sense to define it, and we define it, and you can construct it. Again, this isn't very interesting because the whole application of doing it is to get something weaker than these snarks. So it's not a super good way to go about it, but at least it shows that maybe this is this type of spooky free encryption is the right goal to aim for, and
Can you construct this from IO?
I actually don't know.
But then the last line imply that spooky free homomorphic encryption would require non-standard assumption.
It actually doesn't, because the Aiello et al. Construction, I believe, you could be so not clear.
It's not it's static honest.
Yeah, it's static honest, so maybe actually that we don't have separation for. But yeah. So so the last line is that actually if you build this type of spooky free encryption, you can plug it into this application that I didn't want to talk about building succinct arguments for all of NP. Okay. And the last question is, can we improve the efficiency of multi-key or spooky encryption? So in particular, when you do the homomorphic operations, the ciphertexts are in the expanded form. They're like n times bigger, where n is the number of party than original ciphertext. So the computation takes n times the original circuit size of the function you're trying to evaluate. Is that necessary? Can you do better? So we don't know. Yeah.
Some subset of our subset. Can you get a concrete
You're asking the wrong person. I have no idea. I think, I don't know. Yeah, you can definitely do it with the A.
Maybe you don't need the FHE, which only does local, but maybe you can do a little bit more.
That's right. Yeah. Maybe, essentially, you need to. I'm over time. Okay. Maybe yeah. So.
But it's okay. I mean, people are talking. We're just talking. Do you have any more points to make as a question?
It's, I mean, for the sake of not mentioning only people who are in Europe, it's Sylvia at work, Michael Langberg, Kobe Nissim, and
Thank you. Yeah. So that was the original party that asked this question of spooky free encryption. What? Oh, there's more. Okay, other papers I missed.
Before we ask your last question, in some sense you need to degrade with time polynomial, and so do you mean circuit size plus polynomial in the number of parties, or?
No, I don't see why you need this. So I would like to do so that's right. I don't want circuit size times number of parties. So I want like.
Plus.
Yeah, the circuit, assuming it takes an input from every party, the circuit size is at least as big as the number of parties. So I want just linear in the circuit size. I'm not sure, actually. Yeah. I'll take questions offline. All right. Thanks. Yeah.